دي نوجك another side. You can start, students. You have 20 minutes maximum, so make it efficient, please.
Good day, everyone. I'm MARKONI. Today, our project focuses on indirect evaporative cooling system. Indirect evaporative cooling systems is an energy efficient cooling method that uses evaporation to lower air temperature without adding humidity. This works by transferring heat to the heat exchanger, providing a sustainable and eco-friendly alternative to traditional air conditioning. Nowadays, with the high levels of global warming, the cooling demand
You
is
have
also
to raise your voice. I can't hear anything. Right? Raise your voice so we can hear you.
Nowadays, with the high levels of global warming,
Yes.
the demand for cooling is also increasing. Traditional ACs, on the other hand, provide this cooling but with the cost of greenhouse gas emissions, which furthermore increase the global warming. Our solution to this is indirect evaporative cooling systems, where cooling is provided without any greenhouse gas emissions, therefore not affecting any global warming levels. When it comes to our design objectives, we aim to design a system with a budget of $800. We also ensure that it's robust, cost-effective, and safe for users. We also prioritize sustainability by reducing waste and environmental considerations like reducing pollution and energy consumption. For the constraints, we considered local weather and low water usage for incorporating recyclability. We also, for all costs like installation and maintenance, we made sure that it's within our budget. And finally, we ensured that the project was finished on schedule by careful planning and monitoring. For the review, Amin will.
Hello everyone, I am Amin Faisal. Today I will compare between indirect evaporative cooling IEC and direct evaporative cooling DEC. DEC process uses sprayed water over pads to cool air. Fresh water circulates in a water basin and is pumped back. However, this process increases moisture. On the other hand, ICE cools water indirectly without increase moisture. It separates between cooling process into primary and secondary air. It's transferring heat through a heat exchanger. It allows it to cool below the wet bulb temperature of the surrounding air for primary air. Next. Looking at the psychometric chart, DEC increases moisture with a constant enthalpy, while IEC decreases temperature without changing its humidity. Next. The main advantage of IEC includes cooling without increase the moisture. The disadvantage is reduced airflow, while DEC main advantage is its low cost, but it increases moisture, making it less effective and not suitable for humid climates. Now, Albara will continue with the system breakdown structure.
For the design of the system, we subsystem into three main subsystems. The first one is the electrical subsystem, the second one is the water spray subsystem, and the third one is the structural subsystem. The electrical subsystem includes the axial fan, which uses the inlet and the outlet, the electrical circuit for the water spray, including water nozzles, piping system, and the pump. And in the structural subsystem, we have the heat exchanger frame and water tank and the wooden card. We designed our system using SolidWorks, as you can see in this slide. For the airflow inside the heat exchanger, it follows this schematic. We have the primary air, the top view, and the secondary air. In the inlet, the primary air enters the system, and then it uses this multi-entrance procedure to ensure the uniform distribution of the air along the heat exchangers. In this view, we can see the regenerative part of the system. We have the products when it exits the system. Part of it gets separated and then reintroduced into the system to work as the secondary air. We see in this view how it follows the product air enters the system and then exits and enters again, while water is sprayed at the same time. This air stream will get cold and then transfer its cold energy to the other stream without introducing any moisture to the primary air. For the engineering analysis and design, Gabani will talk about it.
Hello everyone. Today I will be explaining the analysis of our system. So first of all, as you can deduce from the name of the project, the cooling capacity is sourced from the evaporation. So as water evaporates, the energy needed to transfer its state from liquid state to gas state, the energy is taken from the surrounding air. So the temperature of the surrounding air drops. In order to calculate the available cooling capacity, we use this formula, which is the mass flow rate of the evaporation, or evaporation mass flow rate, and the enthalpy of vaporization. So in order to calculate the mass flow rate of evaporation, we first need to calculate the heat transfer coefficient, and from there we can go to the mass flow rate coefficient. To calculate the heat transfer coefficient, first we classified the airflow as flow over a flat surface, and the flow was classified as also laminar using the Reynolds number. Then we can calculate the H using the Nusselt number. From there, after obtaining the heat transfer coefficient, we can move on to evaluate the Lewis factor. And this Lewis factor was taken from a research done for cooling towers. We opted to use this Lewis factor as it has a similar design as our system, because they have airflow over a flat surface. So after evaluating the Lewis factor, we can move on to evaluate the mass transfer coefficient. From there, to evaluate the mass transfer rate, we need to obtain the specific humidity and saturation and the current specific humidity, along with the area and the wettability factor, which was assumed to be 0.95, as most of the surface would be wet. Then, after the evaluation of the evaporation mass flow rate, we can easily obtain the available cooling capacity. This calculation has been done to three separate parts of the heat exchanger, and we only had the inlet temperature. So in order to evaluate the exit temperature for each part of the heat exchanger, we did iterations, and these iterations were so many, so we needed to code it with Python. Thus, and that way, after many iterations, the solution converged, and we were able to calculate and expect a final temperature from the heat exchanger. Now, Albara will continue.
Yes, we performed simple simulation using star TCM plus software to see the airspeed speed inside the secondary and primary air tunnels. This picture shows the contours of the velocity inside the primary air, and this picture shows the pressure drop inside the primary air speed. You can see in this picture, when the air exits the heat exchanger, velocity increases inside the acrylic tunnels until it exits, and here we see the pressure drop also inside the primary airstream. The second image shows the same thing but for the secondary air. Somehow it has the same performance, but the pressure drop is different because the mass flow rate inside this stream is less, not like the primary air. Yes. For the manufacturing and material selection, we performed material selection matrix. According to this matrix, we selected the plexiglass for the following advantages. It has low thermal conductivity, so the system will be somehow will not be affected by the ambient temperature. Also, it's cost effective. It's not expensive, easy to manufacture, and corrosion resistant, not like aluminum or steel. It also had good strength to weight ratio. For the manufacturing, we use this CNC machine to cut the plexiglass sheets according to the drawings, and then we assemble these sheets with adhesive and silicone to prevent the water and air leakage out of the system. After that, we also assemble the piping system according to the following assembly process. You see, we build the water tank and then the outer plexiglass, and then we attach the frame to the heat exchanger. The third step for attaching water tank to the system, and then we would build the wooden cart. We attach the system to the wooden cart, and then we assemble the piping subsystem. After that, we create a hole in the system. We build the electrical circuit and did the ceiling and axial fans and put the axial fault into their place. Yes. The following image shows the system at the final state. You see the axial fan, the electricians, and everything. The cost analysis we see here from the pie chart. The most expensive part were the frame and the water tank, which made out of plexiglass. We also have the heat exchanger and the axial fan also. They had they consume the most out of the voltage. For the testing, Badraldeen will talk about it.
Hello everyone. To evaluate the performance of our system, we have to set up an experimental setup that suitable for different climates. This setup includes the following. First of all, we have the pre-installation checks. This we have to make sure that the system is installed according to our design specification. Then we have to make sure of the piping and the plumbing and electrical connections are connected properly. Then we have to make our safety measures. After that, there is a functional testing. This includes the power and control, water distribution system, and the fan and airflow. After that, we have the leaking and isolation test. We have to make the water does not leak into the system. Then we have the cross-contamination test. This includes that we have to make sure there is no mixture between the air, the wet airstream and the dry airstream. And finally, there is the performance testing. We have made testing for humidity and temperature. At the first test, we did it in the thermal lab. As you see, the ambient temperature was 24 degrees Celsius, and the relative humidity was 25%. In order to the system to reach equilibrium, we have supplied a hot air through a fan air heater to reach equilibrium at approximately 31 degrees Celsius. Then we operated the system, and the temperature dropped until 21 degrees Celsius, achieving a relative humidity of approximately 42%. After that, we have set an experiment room to try to simulate real summer conditions. The room was heated until 32 degrees, but the relative humidity was approximately high. This causes the system to limit the system performance. The temperature only dropped until 25 degrees, and the outlet relative humidity was 74%. After that, we tried to enhance our testing by connecting a duct to the exhaust fan and installing an inlet fan to enhance the airflow. This test was successful to make a temperature drop of approximately 22.49 degrees Celsius, and we reduced the relative humidity into 62%. For this testing, we use control center software and electronic sensors. We measure the outlet and the inlet temperature with respect to time, as you see in this graph. We use different mass flow rates with using the variable of R. We change the R value. The R value is the value of the outlet mass flow rate and the inlet mass flow rate. We change the R value, as you see, make it 0.3, 0.15. The result we have done from this, we have got from this testing, as we see, the cooling capacity decreases gradually as we increase the R value through the testing and through the model. We also notice that as we increase the R value, the outlet temperature increases while the relative humidity decreases. We see in the blue line and the orange line. We also notice that as we increase the R value in the x-axis, the dew point effectiveness and the wet bulb effectiveness decreases gradually. From all the testing we have done, we noticed that the best result was obtained from the minimum R value, which was from the minimum mass flow rate for the outlet fan and the maximum mass flow rate for the exhaust fan. We got a temperature for 22.49 degrees Celsius and a relative humidity of 74, and given value for Q, coefficient of performance, wet bulb effectiveness, and dew point effectiveness. As for the future work, we have concentrated on three main aspects. First of all, we can enhance heat and mass transfer by using advanced material for heat exchanger or by increasing the surface area. We can also enhance our performance by optimizing operational parameters. This includes using high quality nozzles to give an optimal flow rate and an efficient water distribution. We can also use the technique of pre-cooling the inlet air. The third aspect is to integrate our system with renewable energy sources such as solar and wind energy. This is our references. This is our poster.
Thank you.
For listening.